Today's lesson is on the second derivative. All along you've been working out the first derivative. So let's look. If f of x is the function, then the first derivative is f prime x, or we can write it dy by dx. What does the first derivative tell me about? It tells me about the gradient of the tangent to the curve, or we call it the gradient function. The second derivative is really the derivative of the derivative. So you can see there's the double dash over there, x, and we write d squared and y over dx squared. That's just the notation that is used for the second derivative. Notice the d is squared, maybe that's for saying second derivative, and that you differentiating with respect to x twice. So this is called the gradient of the gradient function. Now the first derivative, when you put that equal to naught, then you find the stationary points. Okay, so now we know what to do with the first derivative, we know what it means. Let's focus now on the second derivative. The second derivative talks about the concavity of the function f, and I'll explain that now. Also, the second derivative, if you put that equal to 0, you'll get what we call a point of inflection. That's the point where the concavity changes, and it's used to classify stationary points. So let's apply this now and see how it works. Let's look at this graph here. And I've chosen specifically to look at the graphs that you will soon be working with, and that's cubic graphs. So let me explain what we mean by the concavity of the graph. Concave down. You can see this here when you go. This is called concave down, and at a certain point that concavity changes to concave up. So the point of inflection is where the concavity changes. Let's look at another sketch. This would be concave up. Concave up is happy. Inflection point when the concavity changes, and this would be concave down. Down, I'm feeling sad, it's going down. This is concave up, and this part is concave down. And at the point where the concavity changes, that is called the point of inflection. Now the graph doesn't always look like that. It could look something like this. Note, this is concave down. There's a point of inflection and it goes concave up. So if the second derivative is positive, then f is concave up. So if you work out the second derivative at a certain point and you find the answer is positive, then it's actually saying at that point it is concave up. So you'll have to work out the second derivative. Let's say the question is, determine whether it is, what's the concavity at x equal to naught in the sketch. Then I would work out the second derivative, put naught in here. It will result in a positive answer, and then I can conclude that at x equal to naught, it would be concave up. Okay. And if I stick with this function here, and let's say the question says, discuss the concavity at the point x equal to 2 for this function, then I would work out the first derivative and then the second derivative. So the moment they talk about concavity, I'm going to work out the second derivative. I will substitute 2 into the second derivative, and I will get an answer that is negative. Then I will say f is concave down. Just think negative, I'm feeling down, concave down at that point. If, however, you work out the second derivative and you find it's naught, then f is a point of inflection at x equal to a. So if you look at this sketch here, if I found the second derivative and substitute, it looks like it is at 1, and I get the second derivative equal to naught, then I know that is where the point of inflection is. Let's apply this. Calculating the coordinates of the point of inflection. The first thing you're going to do is going to find the second derivative, put it equal to 0 and solve for x. Once you have the x value, you substitute it to find the y value, and you'll substitute it into the original function. Note the point of inflection is midway between two stationary points. Okay, so here, in this example here, you have two stationary points. In this one also, two stationary points. And it's halfway, so you can actually use the midpoint theorem to find that coordinates there and that there. However, when you don't have two stationary points, as in this case, then of course you're going to have to use the second derivative. But the second derivative works either way. But just to know that it's halfway between the stationary points. In this example, it says determine the coordinates of the point of inflection of f of x equal to x cubed minus 9x squared plus 3x minus 5. So we find the first derivative, apply our law, 3 and x squared minus 18x plus 3. The laws of differentiation. Of course, negative 5 is a constant, so it's 0. Then you find the derivative of the derivative. That's when you call it the second derivative. So this then is 6x minus 18. So for the point of inflection, you put the second derivative equal to 0. So 6x minus 18 is the second derivative equal to 0. Solve for x. X would then be 3. So at x equal to 3, this function has a point of inflection. But we want the coordinates of the point. So we're going to take x equal to 3 and we're going to substitute it into f of x, because that is y here. So substitute it into the original function. So it's 3 cubed minus 9 times 3 squared plus 3 times 3, subtract 5. So I substitute wherever see an x, I replace it with 3. And that gives me negative 50. So the coordinates of the point of inflection is 3 and negative 50. So remember, point of inflection, its second derivative. Put it equal to 0, and then you'd be able to determine it. Let's look how we use the second derivative to classify stationary points. So here we've got the stationary point here. We know at the stationary point, the first derivative is 0. So we've got two stationary points there. And we know when it's concave down, the second derivative is down, it's negative. When it's concave up, the second derivative is positive. So you can see a concave down, it has a maximum. Concave up, it has a minimum. And we call this local maximum and local minimum. So if we continue with this graph further this way, there's obviously maximum points going on and on. But this is a local maximum. Local to this graph, local minimum. Okay. So if we have a stationary point, in other words, if f dash a is equal to 0 and the second derivative is positive, then f has a local minimum at x equal to a. So note here, we're classifying stationary points. So we're looking where the first derivative is 0. So then I found my stationary point here. And then I'm now looking at what is the value of the second derivative. If the second derivative at that x value equal to a is positive, remember, then it's concave up, which means there's a local minimum. So concave up, minimum. If the first derivative is 0 at that point, in other words, if you've got a stationary point, you want to examine that stationary point, you substitute that value into the second derivative. And if the result is negative, then you've got concave down, which means you've got a local maximum at that point. If you have a stationary point and the second derivative is equal to 0, then f has a stationary point of inflection at x equal to a. So here we have a second derivative is 0 and the first derivative is 0. then it is a stationary point of inflection. So both are satisfied, and the graph will look this shape. It obviously can come from this side here, but there will not be two stationary points here. Notice when there's one stationary point, that stationary point will also be a point of inflection. Let's look at an example. That was a lot of information, but if you just remember, I'm up, concavity is positive, second derivative is positive. So visualize that, concave up, I'm positive, it's happy, there's a minimum, local minimum. Concave down, negative, I'm feeling down, second derivative is negative, then I will have a local maximum. And if the second derivative is 0 at the stationary point, then at the stationary point of inflection. Let's look at this example. Here we've got the points, and they tell me these points, 1 and minus 1 and 3 and 3, are stationary points of this function. So if we had to work out the first derivative, put it equal to 0, solve for x, we would have got x equal to 1 and x equal to 3, and of course find the corresponding y values. So here we have the stationary points. It says classify each of these stationary points as a local maximum, local minimum, or stationary point of inflection. So the moment we classify stationary points, we can use the second derivative. So here's the function. So work out the first derivative first. Minus 3x squared plus 12x minus 9. Applying my laws, 3 gets multiplied by that coefficient is minus 3, 1 less. 2 times 6 is 12, 1 less than the exponent. 1 times minus 9 is minus 9, and 1 less than the exponent. And this is a constant, which is the derivative of 0. The second derivative is the derivative of the first derivative. So in other words, you differentiate again for the second time. So this is minus 6x and plus 12. So now we're examining this stationary point. So x is equal to 1, because that's where the stationary point is. They said that in the information. So f double dash 1 is equal to, substitute 1 into the second derivative, minus 6 times 1 plus 12 equals 6. It's positive, so it's happy. And therefore we can say it as a local minimum at x equal to 1. Again, test the other points. Substitute x equal to 3 into the second derivative. So it's minus 6 times 3 plus 12, which results in negative 6. It is negative. It is concave down, and therefore it has a local maximum at x equal to 3.